Uh, Thanks. I'm Osbert Bastani, and today I'm going to be talking about some of our work on verifying fairness properties for machine learning models. This is joint work with Zhang and Armando Solar-Lezama. So as I'm sure you all know, over the last decade or so, a lot of real-world software systems have increasingly been relying on machine learning components. And as a consequence, we really need to start thinking about how to verify desirable correctness properties for these systems. So we're going to be focusing on a property called fairness, which has been identified as a really important property in a lot of applications. And basically this property says that some machine learning model, in some sense, should not discriminate against minority populations. So as an example, if you have a machine learning model that's used to help make financial or legal decisions in some context, you want to make sure that these models don't discriminate based on sensitive attributes such as race or gender. And alternatively, if you have tools like speech recognition or facial recognition based login, you want to make sure that these tools work equally well for kind of the standard user as for people with different kinds of accents or different kinds of facial features or so forth. And actual issues have already been shown to in both of these kinds of settings for machine learning models deployed in the real world. So at a high level, our goal is to design a verification algorithm that takes as input a machine learning model and basically spits out whether the model is fair or unfair according to some formal definition of fairness. So there are two existing approaches that have addressed this issue. The first one is based on static verification. And basically, they reduced the problem of checking the fairness property to a sequence of max SMT calls. And roughly, they're trying to compute an integral of a property of a quantity in the fairness definition. So this technique doesn't really scale to realistic machine learning models because these max SMT calls tend to be very expensive. And in their benchmarks, the largest one they can scale to is a neural network with just 3 neurons. Also, because they're using a symbolic approach, they're quite limited in the kinds of programs they can represent. For example, they can't represent programs with loops. An alternative approach is based on testing. So basically, the idea here is to use randomly sampled individuals to estimate whether or not fairness holds. Unfortunately, this approach, so it scales really well to large programs because it doesn't need to worry about it only needs to execute the programs. It doesn't need to symbolically analyze them. But unfortunately, they don't provide any theoretical soundness guarantees. So our approach is going to be to try to build on the testing approach, so design an algorithm using random sampling to check fairness, but then try to actually provide some theoretical guarantees. And to do so, we're going to use ideas from the statistical verification literature. And they basically use statistical tools called concentration inequalities to bound the probability of false negatives. So basically, you can get a bound on the probability if, assuming algorithm A says that some model F is correct, then you can bound the probability that F is actually correct. So we want F to be correct with high probability if the algorithm says that F is correct. And this can be interpreted as a probabilistic notion of soundness. So it's weaker than the traditional notion of soundness, unless you set delta equal to 0. So if delta equals 0, then this basically says that the traditional soundness property, if the algorithm says F is correct, then F is guaranteed to be correct. For sampling-based approaches, we can't actually get delta equals 0. So some error is always going to be inevitable. But we can make delta as small as desired by taking n, the number of samples, to be sufficiently large. So our approach, as I said, is going to build on these techniques. But we're going to improve them in 2 ways. So first of all, the existing techniques can't actually be used to obtain probabilistic, an analog of a probabilistic analog of precision. Basically, that says that gives a bound on the probability of false negatives, but our technique will actually be able to do so. And second, existing techniques can actually handle most commonly used fairness properties because they're arithmetic properties. And we'll see what that means in a second. But our techniques will extend the existing tools to be able to handle these kinds of properties. So next I'm going to give a brief background on fairness. And most of these ideas come from most of these definitions come from the machine learning literature. So at a very high level, the idea in fairness is that we have a decision-making model. We have two subpopulations, a majority and a minority subpopulation, and they're both being fed to the same decision-making model, which is making some decisions, such as whether or not to offer a job candidate a job. And we want to make sure that in this context, the decision-making model is not discriminating against the minority subpopulation. So just to formalize this setup, we assume that we have a distribution, a probability distribution over individuals, which is called the population model. And one component of the individual attributes is a sensitive attribute, A, which indicates whether they're from the majority or minority subpopulations. And we're also given a binary classifier. For example, F might be a learned neural network, and it basically maps individuals to outcomes where 1 indicates a positive outcome and 0 indicates a negative outcome. And in this context, there have been a bunch of fairness properties proposed in the literature. I'm not going to go into details in all of them, but the main point is that for different domains, we actually need to use different fairness properties. So in this talk, I'm going to be focusing on demographic parity, but our techniques actually apply generally. So demographic parity is a property which basically says that majority and minority members should get positive outcomes at roughly the same rate. And just to formalize that, we first define the acceptance probability for subpopulation A to be mu A star. And this is just the probability that a member from the subpopulation A is given a positive outcome. And then a classifier F satisfies demographic parity if basically the ratio of the acceptance probability for the minority group divided is a constant factor of the acceptance probability for the majority subgroup. So that's just captured by this indicator Y parity star. So this value indicates whether or not F satisfies demographic parity. So there is a constant C in here, and that's domain specific and has to be chosen by the user. So now we have a notion of fairness. So we can kind of we can formalize the fairness verification problem a bit more. And just to make things a bit concrete, we're given a population model. It can be in any form, but here we've shown one in the form of a probabilistic program. So it just basically what we can do is we can take samples from this program. And then we have on the right-hand side, we have a classifier which basically takes a sample from the population model and outputs whether or not that sample should be given a job. And the question we want to answer is, does the classifier, together with the population model, satisfy demographic parity? So next, I'm going to talk about our fairness verification algorithm. So first, I'm going to give an overview and then go into some of the detailed steps of how the algorithm works. So at a high level, our algorithm iteratively collects new samples and then tries to check for fairness. So here, N represents the number of samples that have been taken by our algorithm so far. And on each step, we're going to sample an individual from each subpopulation. So for one from the majority subpopulation and one from the minority subpopulation. And then we're going to compute a fairness estimate. So this is an estimate of the Y parity star from the previous slide using our N samples from each population. So that's the first step. And on the second step, we're going to compute a statistical guarantee on how good of an approximation Y parity hat is compared to Y parity star. So in particular, we're going to compute this parameter gamma, which kind of lower bounds the probability that the estimate is equal to the true value. And if we get a gamma that's sufficiently small, so here delta, big delta is a confidence parameter given by the user, then we return y parity hat. And basically our algorithm will just keep iterating until it gets, until it can get a sufficiently high confidence, and then it'll return. And as we take n larger and larger, our statistical guarantee gets stronger and stronger, and eventually we can prove that this algorithm will return the estimate. So the first step, just going into some more details on the first step. So how do we estimate the fairness parameter? How do we estimate whether or not the model satisfies fairness? The basic idea is that given n samples given our n samples, we're just going to estimate mu a star using mu a hat, which is just the empirical frequency with which the members in our samples are given positive outcomes. So this is an estimate. And then once we have this estimate of mu a star, we can actually just plug it into the estimate, to the formula for y parity star to get an estimate of y parity star, which we call y parity hat. And then so this is the estimate computed on the first step of our algorithm. So the second step is trying to get a statistical guarantee on the probability that y parity hat is equal to y parity star. So to do this, we proceed in two steps. So first, we're going to determine how well the mu a hat approximates mu a star, and then we're going to determine how well y parity hat approximates y parity star. So to determine the first thing, we're going to or the standard approach would be to use Hofting's inequality, and basically Hofting's inequality can be applied to Bernoulli random variables. So letting mu star be the probability that a Bernoulli random variable x is equal to 1. Then Hofting's inequality bounds the error of an estimate mu hat of mu star using IID samples. And we can apply this inequality to our setting because mu a star is actually exactly the probability of a Bernoulli random variable, since f of v, here f of v is a Bernoulli random variable because it takes values in 0 or 1. And when we apply Hofting's inequality, we get this formula, which basically says that mu a hat is a good estimate of mu a star with high probability. So here epsilon is the good estimate portion of the bound. So that says that mu a star is close to mu a hat. And then the part in blue is the high probability part of the bound. So this says that as the number of samples n gets large, we can get as close as we want to mu a hat being a good estimate. We can get as close as we want to that holding with probability 1. And this theorem actually holds for any epsilon less than or equal to, any epsilon greater than 0. So you can plug in whatever value of epsilon you want and get some kind of guarantee here. So the standard approach to doing statistical verification would be to use Hofting's inequality to obtain a statistical guarantee. And basically the only thing we have to do is choose epsilon, and you can do this in a way so that it's possible to get the confidence threshold that we want. I'm not going to go into the details of exactly how this works, but you can look at our paper for that. The key shortcoming of this approach is that the number of samples in Hofting's inequality must be chosen beforehand. So we can't kind of choose different numbers of samples and see if it holds. Hofting's inequality then would no longer hold if we did that approach. And therefore, as a consequence, we can't actually achieve probabilistic precision because we can't know ahead of time how many samples we need to achieve both probabilistic soundness and probabilistic precision. And therefore, we're actually going to use a much more recent adaptive variant of Hofting's inequality, which basically lets us do our approach of increasing n over time until we get a result that we're looking for. And this theorem, it basically looks exactly the same as Hofting's inequality, except the values of epsilon the value of epsilon is adjusted so that the value of delta here is adjusted so that to account for the the fact that we're taking a sequence of checks rather than just doing one check with a single value of n. And then as before, we can just stop once we successfully get the confidence that we're looking for. So now we have a bound, the first part on how good of an approximation mu a hat is for mu a star. So we still need to get a bound on the fairness property, how good an approximation y parity hat is for y parity star. And basically to do this, we devised a set of inference rules that let us, given the guarantee for mu a star, we can derive corresponding guarantees for arithmetic expressions of mu a star. And y parity star is an arithmetic expression of mu a star, so you can use these inference rules to derive the desired bound. Again, I'm not going to go into details about how these inference rules work, and you can see our paper for details on that. We also proved that our algorithm satisfies probabilistic soundness and probabilistic precision, as I defined above. We additionally prove a probabilistic completeness notion, which says that under some mild assumptions, with probability 1, our algorithm is guaranteed to terminate after finitely many steps. So we evaluated our algorithm on two benchmarks. So first, we evaluated on the FairSquare benchmarks. So we compared to FairSquare on the FairSquare benchmarks from their paper. Also, to demonstrate scalability to real-world machine learning models, we used it to verify a fairness property for the quick draw benchmark. So just to give some details, the FairSquare benchmarks are a collection of 39 relatively small problem instances. So they consist of a pair of a population model in the form of a Bayesian network and a machine learning model, which includes neural networks, decision trees, and SVMs. However, these benchmarks tend to be very small. For example, the largest neural network in their benchmarks has just 3 neurons. And for the FairSquare benchmark, we used big delta equals 10 to the minus 10. So that means that our soundness and precision guarantees hold with probability at least 1 minus 10 to the minus 10, which is very close to 1. And the fairness parameter C, we just took from their paper. We also, and then for the quick draw benchmark, this is actually a neural network model that's used to predict the object category of a human-drawn sketch. For example, we just used the binary outcome dog versus not dog. The sensitive attribute we used is whether or not the human who drew the sketch is a user from the US or a non-US user. And then we have these are state-of-the-art neural network architectures, and in particular, they're much larger than the FairSquare benchmarks. So the largest one is 5 orders of magnitude larger than the largest FairSquare benchmark, and we use the same parameters. So just to give some results, on the FairSquare benchmark, our approach outperformed FairSquare on 30 out of 39 of the problem instances. And in particular, we scale much better to large problem instances. So FairSquare fails to solve 4 problem instances after a 900-second timeout, whereas our tool solves all 39 in within 200 seconds. So the main reason that our tool actually failed to outperform FairSquare on 9 of the benchmarks is that the FairSquare benchmarks were implemented in Python, and our tool actually, it's repeatedly running this code. So it's very sensitive to the language in which these benchmarks are written. So we can actually speed up our tool by translating the benchmarks from Python to C. And just to give 2 examples of how that works, we translated the slowest benchmark relative to FairSquare. So we were slower than FairSquare on this benchmark. And we actually got a 300x speed up compared to the uncompiled benchmark. And after that, we were also 10x faster than FairSquare on this benchmark. We also showed that for the slowest benchmark overall, I think it originally ran in 190 seconds for Verifair, but we actually sped it up by 300x again. So next, on the quick draw benchmark, we again ran our verification tool for this benchmark, and verification terminated in 606 seconds using 28,000 samples. We also did a study of how the running time depends on various parameters, but I'm not going to go into that due to lack of time. So just to conclude, I really think, so software is really starting to use more and more learning-based components, and it's really important, I think, that we develop new techniques for verifying these kinds of software and the corresponding properties that we care about. And I think fairness is one of the key properties. In addition, there are also other important properties such as robustness, safety, and so forth that are also important. So future work on our approach includes trying to improve the sampling strategy when rejection sampling performs poorly, and also adapting statistical verification to check properties beyond fairness. Okay, so thanks for listening, and I'll be happy to take any questions. Yeah, sure. So in this plot, we were actually, so if you look at the formula for Y parity star, it's really, so the key kind of challenge in this formula is when the numerator and denominator, when that ratio is really close to 1 minus C. So basically when fairness just barely holds, it becomes really hard to check whether, it becomes really hard to get good bounds on whether this inequality goes one way or the other. So that parameter of C happens right here. And that's why you kind of get a blow up in the running time, because you need to take a lot of samples to get good bounds on that inequality.
Hey, it's very, very cool. So when you have, so when you judge something to be unfair, are you able to, maybe with the samples you have, give any information to the machine learning expert on how to change their model or something to do there?
That's a very good question. So right now, that's not something we've looked into. You can look at the samples in aggregate that, from the models to see like what kind of samples might be causing the unfairness. But yeah, I think in general, like trying to debug these models is a very different question than the one we've been looking at. So I think it would have to rely on something more than just what we have here.
Thanks.